Richard James Mathematics Resources will continue Grade 4 Practice Paper 1 with Part B. And this will be the second set of 12 problems that we will be solving. And we means Jerry and I. So let us start with question number 13. Remember that for the first 3 videos, the number of problems that we will solve is 12 in each section. So we will begin at number 13 in this section. What is the least common multiple needed to add the fractions 2/3 and 3/4? How do we know the least common multiple needed to add those fractions? When we are adding fractions, we need the least or lowest common multiple of the denominators. Therefore, in solving this problem, we will focus on the denominator. So the greater portion of the manipulation of the fractions that we will be looking at in this problem will be with the denominators. Not only that, we are not required to add the fractions. We are only required to tell the least common multiple needed to add the fractions. And we therefore need to take a look at the lowest common multiple of the denominators. When adding fractions, we need the least, or we may say lowest common multiple of the denominators. Let us take a look at the fractions. There we have the 2 fractions. So I'm asking Jerry, we need the least common multiple of which 2 numbers?
3 and 4.
Right, 3 and 4. We need the least common multiple of 3 and 4 because they are the denominators of the fraction. But we are not leaving anything up to chance. We have right there our fraction bar. So a fraction is comprised of 3 sections. The first one that we are looking at is the fraction bar, and this is the bar or line segment that separates the numerator from the denominator. So we have the numerator, we have the denominator, and we have the fraction. Right, we have the fraction bar. Now, some students attempt to write fractions by using the lines in their notebook or on the folder leaf as the fraction bar. Even though lines are there, you need to include the fraction bar. You have to be deliberate. You have to be explicit. You have to make sure that you show a fraction bar, and you should not allow your marker to assume that the bar or the line that is in the book already is being used as a fraction bar. You need to put down your fraction bar, because when you are writing, you generally write in consecutive lines. Therefore, your marker will think that you just have information in one line and you are just putting information in the other line. So your fraction bar is important so that you show deliberately to your marker that you intend to write a fraction. For the addition of fractions, we need to pay special attention to the denominators. And what are the denominators, Jerry?
3 and 4.
Okay, good. Those are your denominators, 3 and 4. We have them highlighted right there, your denominators, 3 and 4. And of course, we have your fractions labeled, as we will do on numerous occasions, in order that you will always be aware of the 3 parts of a fraction. We will proceed to find the LCM of 3 and 4. What is the least common multiple needed to add the fractions 2/3 and 3/4. And I am saying to you that what least common multiple we need is the least common multiple of the denominators, and the denominators are 3 and 4. We need the least common multiple of the denominators. What does that mean? To answer this question, let us first look at two key words. And I see Jerry with his scratch pad, and he would have already discovered the least common multiple that we need. So what is the least common multiple that you have there, Jerry?
12.
Okay, so 12 is what he has, and 12 is actually the correct answer. But we will continue with this slide in order to demonstrate to everyone, not only Jerry, who is very quick at it, but some students who may take a longer time to work it out. So we will take a look at two keywords, common and multiple. What does common mean? What is a multiple? If a property, characteristic, or something is common to both denominators, then it is present in both of them or related to both of them. Since we are talking about multiples common to both 3 and 4, any number that we will be using or taking as the least common multiple in this particular case must be a multiple of 3, and it must be a multiple of
4.
Right. So common means that it is present in all. In mathematics, that's what it means. If something is common to 3 and 4, it means that it is related to 3 and it is also related to 4. So when we say common multiple of 3 and 4, it must be a multiple of 3 and it must be a
Multiple of 4.
Alright, so it must be a multiple of 4 also. A multiple of a number, let us say n is a number. A multiple of a number n is any number that n can divide into without leaving a remainder. So a multiple of n is any number that n can divide into without leaving a remainder. The number is therefore divisible by n. Divisible means that it can divide into without leaving a remainder. That is what we mean when we say something is divisible. With all of that, we will go through a lot of demonstration in order to explain everything in great detail. So we have multiples of 5. Multiples of 5 will be what? Those numbers that 5
Can
divide into
with a remainder.
without leaving.
A remainder.
Alright, so without leaving a remainder. 5 can go into those numbers without leaving a remainder. And we have taken some of them. 5, 10, 15, 20, 25, 30. 5 can go into those numbers without leaving a remainder. And here is where the multiple is related to multiplication. Because if we are saying our multiplication table, what do we say, Jerry? 5 ones 5, 5 twos 10, 5 threes 15, 5 fours 20, 5 fives 25, 5 sixes 30. Right. So in our multiplication table, we find the multiples of 5. All of those numbers are multiples of 5 because 5 can divide into them without leaving a remainder. We may also say that all of those numbers are divisible by 5. Divide, divisible. Why do we use the words that we have there that are related to the word divide to explain multiples? We have these words, divide, divisible. Why do we use those words that are related to the word divide to explain multiples? When the word multiple is related to the word multiply. We will explain that later after we take a look at the real reason for calling them multiples. But at the same time, we cannot give you an idea just now by saying 5 can go into each of these without leaving a remainder, yet still all of these are related to the multiplication table of 5. So the 5 times table will generate all of these numbers that we have here. So it should not be difficult for us to understand why in our definition we have the word divide, but we are talking about multiples, because all of these are multiples of 5. 5 can divide into them without leaving a remainder. Also, they are numbers in the multiplication table of 5. Multiples are what we get when we multiply by the members of the set of natural numbers. The set of natural numbers are also called the set of counting numbers, right? If we multiply by the members of the set of natural or counting numbers, the results that we will get are multiples. So let us take a look at that. Write down some natural numbers. Write down some counting numbers. Because natural numbers and counting numbers are the same. So we have 1, 2, 3, 4, 5, 6. Oh, we'll stop at 6 on this occasion. Because we cannot write down every single natural number, can we?
No.
Because we will be counting forever. So we are taking 6 of them. So there we have just 6 natural numbers. What do we notice? This kind of a special looking N. The symbol that we have above, which is the one that we have right there, the one that we have above the natural numbers, otherwise called counting numbers, is the symbol for the set of natural numbers. It is N. It is an N, and that N is written in a special way with a double diagonal stroke. So we have the N written with a double diagonal stroke, and that represents what? The set of natural numbers. If we want multiples of 5, we may take those natural numbers and multiply each of them by
5.
Right, so we multiply each one of them by 5, and we will get multiples of 5. So do that, which is no different from the set that we had before. So we have these natural numbers, multiply them by 5, what do we end up with? 10, 15, 20, 25, 30, and all of those are multiples of 5. 5 can go into them without leaving a remainder. Each one of them is a multiple of 5. All of those numbers are multiples of 5, as we discussed before. So we know what we mean by common, that it is present, related to all, and we know what multiples are, but we will go for more work in multiples. In order to find multiples of 8, or for that matter, multiples of any number, we take that number and multiply by members of the set of counting numbers. Right. So if we want multiples of any number at all, we take that number and we multiply by members of the set of counting numbers, and we will get multiples. So write down some natural numbers, the same natural numbers that we had before. Right. And if we want multiples of 8, what do? We take those natural numbers and multiply by 8. To get multiples of 8, we multiply those natural numbers by 8. So those are the multiples of 8. And notice that 8 can go into each of these without leaving a remainder. All of those numbers are multiples of 8. The set of natural numbers is not limited to those numbers that we have there. Furthermore, we may choose our natural numbers without listing them in any particular order. Let us take a look at that on the next slide. Okay, here's our question to Jerry. We have what we call natural numbers here. Okay?
Yes.
Alright. Now what we need is natural numbers. Can you tell me some natural numbers that are not here? As long as it is a counting number, is a 7, what else? 8, 9,
10.
right. What about if we don't go in any particular order? Can we use some other natural numbers without going in any particular order?
Yeah.
Like? Give me some of them.
16,
16,
24,
24,
32,
32, right. So we can use natural numbers that are not listed like we have there. So Jerry has a very good understanding of natural numbers. On this occasion, we will take just any members of the set of counting numbers. So let's see, we are choosing some at random. Let's go again. 11, 13, 28, 5, 7. So we are taking some members of the set of counting numbers. And what do we do with them? Multiply by any other member of the set of counting numbers. So if we multiply by any other member, what will be the result? So we have them right there. So we have 11 sixes, 66, 8 tens, 80, 13 twos, 26, 20 fives, 100, 5 12s, 60, 7 nines, 63. Right. So we are multiplying members of the set of counting numbers. The result is not only a multiple of the second number, but a multiple of the first number also. So when we multiply 11 by 6, we get
66.
right. 11 is a factor of 66. Or we may say, because we are talking about multiples now, 66 is a multiple of
6,
and 66 is a multiple of
11,
and what do we say? 26 is a multiple of
13,
and 26 is a multiple of
2,
right. 80 is a multiple of
10,
and 80 is a multiple of
8,
100 is a right is a multiple of
5,
and 100 is a multiple of
20,
right. 63 is a multiple of
9,
and 63 is a multiple of
7,
right. 60 is a multiple of
12,
and 60 is a multiple of
5,
right, because when we multiply 5 by 12 we get 60. So 60 is a multiple of 5 and 60 is a multiple of 12. What do we know? We are making sure that when we are through, students have no difficulty in understanding multiples. This might surprise you, but it does not surprise Jerry. Let me see if it surprises Jerry. 66 is a multiple of 11 and 66 is a multiple of 6. Is there any other number that 66 is a multiple of?
no, yes,
What are they? What other numbers can go into 66 without leaving a remainder? Any other number you know can go into 66 without leaving a remainder? What are they? What are they? 33, 22,
and 1.
1, but we're not specifically speaking about 1, although 1, I think that 1 is going to be listed. What else? 2,
3.
and 3. Good. So all of those can divide into 66 without leaving a remainder. So 66 is a multiple of all of those numbers. If two numbers multiply to give a result, then one number may divide into the result to give the other number. So we have 66. Notice that what we have here is 11 times 6, and that is equal to 66. Therefore, 66 divided by 11 is equal to
6.
And 66 divided by 6 is equal to
11.
Right. What about this one? 8 times 10 is equal to 80. So 80 divided by 10 is equal to 8. And 80 divided by 8, 10. What about this one? 13 times 2 is equal to 26. 26 divided by 2 will give what?
13.
Right. And 26 divided by 13 will give?
2.
Okay. There you have it. What about the other one? 20 times 5 is equal to?
100.
Right. 100 divided by 5 is?
20.
And 100 divided by 20 is?
5.
Right. So there we have it. What about 60? 5 times 12, 60. 60 divided by 12,
5 times.
and 60 divided by 5,
5 times.
and
12 times.
right, and 60 divided by 12 is going to be 5 times, and 60 divided by 5 will be 12 times. So when we multiply two numbers and we get a particular result, if we divide one number into that result, we will get the other number. And that is clear. So 9 sevens, 63. Therefore, 63 divided by 9 will give?
7.
And 63 divided by 7 will give?
9.
Okay. The number 66 is not only a multiple of 11 as we discussed earlier on.
Right.
It is also a multiple of 6. Why? Because 11 times 6 is equal to 66.
Yes.
That makes 66 a multiple of 6 and also a multiple of 11. Right. But it is also a multiple of any other natural number that can divide into it without leaving a remainder, or any other natural number that it is divisible by. So 66 is not only a multiple of 11 and 6, it is also a multiple of any other natural number that can divide into it without leaving a remainder, or any number that it is divisible by. So 66 is a multiple of 1, 2, 3, 6, 11, 22, 33, and 66. Apart from 8 and 10, do we know any other multiple of 80, Jerry? Any other number you know can go into 80 without leaving a remainder?
Yes.
What are they?
20.
20,
40.
40,
2.
2,
4. 16.
right, that's a good number of them. So 80 is not only a multiple of 8 and 10, it is a multiple of any other number that will divide into it without leaving a remainder. Numbers like 1, 2, 4, 5, 8, 10, 16, 20, 40, and 80. What about 20 times 5 is equal to 100. Well, I think that Jerry just got a glimpse of that one. Jerry saying that he did not see. He's trying to trick me that he did not see. All right, so let's say apart from 20 and 5, 100 is a multiple of what other numbers? 1, 2, 4, 10, 20, 25, and 100.
And 50.
Right, we have 5 right there, and 50 is the other one. Let's see. So, 100 is a multiple of all of these numbers. 60, as we will think of 60 as a small number, but 60 maybe has more numbers that it is a multiple of than 100. And we had better be familiar with this word from now on. Factor. For example, we know that 100 is a multiple of 1, 2, 4, 5, 10, 20, 25, 50, 100. It means that these numbers are factors of 100. So because 100 is a multiple of all of these numbers, then these numbers are factors of 100. So let's go. Can you tell me, beginning at 1, without leaving out any of them, numbers that can divide into 60, Jerry, without leaving a remainder, all the way up to 60? Let me see if you can tell me every single one of them. Let's go. 1, 2, 3,
5.
you left out 4. Alright, so we have 4, 5.
10. 6.
Right, so 6,
20.
10. You said 10 already, and you say 20. What about these?
12.
And what else? 15.
30.
Right, you said 20 already, so you are going to say 30.
Yes.
And then you'll say what?
60.
Then you say 60. So we have a lot of them. 60 has a lot of factors. There are many numbers that 60 is a multiple of. So 60 is a multiple of all of these numbers that we have there. 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. So you see right there, that is a very old and wise reason for dividing your time into what? 60 seconds in a minute, and 60 minutes make an hour. Because 60 is a very flexible number. It has a lot of factors. There are actually many numbers, maybe more than 10, that 60 is a multiple of. So 60 is a multiple of all of these numbers. All of these numbers are factors of 60. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have quite a few of them. What about 63? 63 is a multiple of 1, 3, 7, 9.
And 21.
Okay. So 63 has a few factors. So there are quite a few numbers that 63 is a multiple of. So 63 is not only a multiple of 7 and 9, it is also a multiple of 1, 3, 21, and 63. 1. Take note of these very important facts. Every natural number is a multiple of 1. Every natural number is a multiple of itself. A multiple is the result of multiplying by a natural number or counting number. A number is a multiple of any other number that it is divisible by. So a number is a multiple of any other number that it is divisible by. So 80 is divisible by 8. That means it is a multiple of 8. So we see here how divisibility is related to multiples. And we have no difficulty in defining a multiple by using the word divide and its derivatives. We need the least common multiple of the denominators. That is the smallest number that 4 and 3 can divide into without a remainder. So we need what? The least common multiple of the denominators. We are still answering this question. What is the least common multiple needed to add the fractions 2/3 and 3/4 or 3/4? Right. And we need the least common multiple of the denominators in order to be able to do that. Therefore, we need the least common multiple of what are the numbers? 3 and 4. And we may do that by taking a look at the multiples of 3 and the multiples of 4. Right. So multiples of 3, no doubt, we know those numbers that 3 can divide into without leaving a remainder, or we may say numbers that are formed by multiplying 3 by a counting number or a natural. Right, Jerry remembers that natural numbers are actually counting numbers. Multiples of 4. 4, 8, 12, 16, 20, 24. In the list, identify the smallest number that is both a multiple of 3 and a multiple of 4. Identify those numbers that are multiples of 3 and multiples of 4. So any number that is in the list of multiples of 3, and it is also in the list of multiples of
4.
What number is that?
12.
Right, 12 is in the list of multiples of 3, and it is in the list of multiples of 4. Therefore, 12 is a common multiple of 3 and 4, because 12 is in the list of multiples of 3, and it is also in the list of multiples of 4. It means that 12 is a common multiple of 3 and 4. The answer is 12, and it is represented by option D. Now we have a serious problem right here. Of course, we need the least common multiple needed to add the fractions 2/3 and 3/4. We therefore need the least common multiple of 3 and 4. Is that right, Jerry?
Yes.
All right, that's right. But we have the list of multiples of 3, list of multiples of 4. Which number is common to both lists?
12.
12 is present in both lists. Therefore, 12 is a common multiple of 3 and 4. But do we need just any common multiple of 3 and 4?
No.
Which one do we need?
The least.
All right, so we need the least common multiple. Is there any multiple in the list that is smaller than 12?
No.
Right, there is no common multiple that is smaller than 12. Therefore, 12 is the smallest or least common multiple of 3 and 4, and that is represented by option
D.
Right, so option D is correct. Without going through the process, we could have identified the correct answer. Why? Because 12 is the only number in the options that 3 and 4 can divide into. See that?
Yes.
So without going through a long, lengthy process, we could just look and see 12 has to be the correct answer. Why? Because 12 is the only multiple of 3 and 4 that is present here. But you would not know if you did not know that the least common multiple that you need is the least common multiple of 3 and 4. And you still would not know if you do not understand what is a multiple and what do we mean by common. Right, so we had to go through all of those processes in order to explain those significant things. We may take another approach in which we use repeated division in a table to obtain our answer. So we may take another approach to it, and the approach that we'll take is to use repeated division in a table. So we have the table, and what do we have in the table already?
3 and 4.
3 and 4, and those numbers are the denominators of the fraction, and we are about to find the least common multiple of those. So we seek, when we are using this method to find the least common multiple, we need to begin by using the smallest prime number that can divide into 3 and 4. The smallest prime number. And the smallest prime number that we have that can divide into either, not into both of them, either one. If it can go into 3, we can use it. If it can go into 4, we can use it. So it is not necessary for us to have the prime number that can divide into both, but if it can divide into any of them. So the one that we will use is the least or the smallest prime number that we know, which is 2. 2 is the smallest prime number. Can 2 work?
No. Yes, it can work for the 4.
Right. It cannot work for the 3, but it can work for the 4. Right. It can work for the 4. Because it can work for the 4, we can use it even though it cannot work for the 3. So we seek the prime number to be used to divide in numbers. At least one of the numbers, which is 4, is a multiple of 2. We may therefore begin with 2, because 2 can divide into 4 without leaving a remainder. 2 cannot divide into 3 without leaving a remainder, and when we have a situation like that, we return the number just as it is. So 2 into 3, not going to go without a remainder.
Right.
It can, but not without a remainder. Because when we divide, we will get a remainder, we do not use it. Or we say that 3 is not divisible by 2, so we put 3 down. What about 2? 2 into 4?
2 times.
2 times, so we put the 2 right there. Can we use 2 again?
Yes.
Why?
Well, it's not going to leave a remainder.
Because 2 can go into 2 without leaving a remainder. Right. So, again, 2 cannot divide into 3 without leaving a remainder, so we will return the 3 as it is. Then 2 into 2 will give 1. What do we use next? Do we use 2 again?
No.
No. 2 cannot go into 3 without leaving a remainder. And when we get 1, it means that the column is exhausted. That means it is finished.
Yes.
So we cannot bother about that column again. The one that we need to pay special attention to is the one with the 3. So what do we use as our next prime number?
1, 0, 3.
Right, so the next prime number that we will use is 3. Because 3 can divide into 3 without leaving a remainder. So on this occasion, the results may not be divided by 2 without a remainder. We therefore move to the next prime number, which is 3. It will work because there is at least one of the numbers that 3 may divide into without leaving a remainder. So we use 3. So we say what? 3 into 3 will give 1. So this column is exhausted and this one is exhausted. How do we know when a column has been exhausted, Jerry?
because we have one at one end and one at the other end.
Right, because there's a 1 at one end and 1 at the other end. So we know that they are both exhausted. So we are finished with the column. However, we generally do not leave them uneven, but we will bring down the one that we have there. Like that. So the other column has been exhausted already. So there we have our lowest common multiple. The LCM of 3 and 4 is the product of those prime numbers. So when we arrive at the numbers here, we use them to form our lowest common multiple by multiplication. So 2 times 2,
4.
And 4 times 3,
12.
Right, so that is how we will arrive at our 12, multiplying all of these factors that we have here, and the result is 12. Therefore, 12 is the lowest common multiple of 3 and 4, and that is represented by option D. Here we have another problem. 8 sweets were shared among 3 children. Michael got 1/8, Wayne got 3/8, and Brittany got 4/8. Who got the most sweets? It is just easy for Jerry to just look at that and tell us which one got the most sweets. Which one?
Brittany.
Right, Brittany got the most because she got 4 sweets out of the 8. However, we will take the time to highlight the principles that will be used to solve the problems. Therefore, you will understand mathematical principles and be able to apply them to other situations. In solving this problem, let us consider the children and the share that each one got. The share that each one got. Michael got
1/8.
Wayne got
3/8.
and Brittany got
4/8.
right. According to what we have in the statement of the problem. We also need to consider parts of the fractions and what they mean. So we remember that we have our parts of the fraction. What's that? Fraction bar. What's that one? Numerator and?
Denominator.
Right. So we have more fraction bar, numerator and?
Denominator.
Right. So each fraction has its fraction bar, numerator and denominator. Each denominator tells us the number of equal parts that a whole is divided into. So if you are about to share something, if you use a particular denominator, then the denominator tells us the number of equal parts, not just the number of parts. Not just the number of parts, but the number of equal parts. The parts must be equal, that the entire whole is divided into. And we will solve the problem by saying that each sweet is a part of the whole, but for the first part, we will solve the problem by making use of a single object. And we will divide that single object into 8, just 8 parts? 8 equal parts, right? So we have our denominator. What is our denominator?
8.
8 is our denominator. And the denominator tells us the number of equal parts that the whole is divided into. The denominator is 8. This means that the whole is divided into 8 equal parts. Let us look at an object that is divided into 8 equal parts, because the 8 that we have here tells us that it is divided into 8 equal parts. There we go. That's nice. 8 equal parts. How do we know that we have 8 equal parts, Jerry?
Because the sweets is sharing
With a denominator of 8. So we know that we have 8 equal parts. So let us count them.
1, 2, 3, 4, 5, 6, 7, 8.
Right, so we have 8 of them. So the entire thing is divided into 8 equal parts. Each of the 8 equal parts is called an eighth. Right? Each one is called an eighth. Each one of the 8 equal parts is called an eighth. An eighth. So 1/8, there's another one. Each part is called an eighth. The whole has 8 equal parts, each of which is called an eighth. It therefore has 8 eighths. So there are how many eighths in a whole?
8 eighths.
Right, there are 8 eighths in a whole. The numerator tells us how many of the equal parts we are talking about. So the denominator tells us that it is divided into 8 equal parts. And the numerator tells us the number of those equal parts we are talking about. So when we say 1/8, we are talking about one of those parts. When we see 3/8, we are talking about 3 of those parts. And when we 4/8, we are talking about
4 of those parts.
right, so 4 of those parts we are talking about. And the denominator tells us how many of them in all. The numerator tells us how many of the 8 equal parts we are talking about. That is, how many eighths we are talking about. Because each one of those 8 equal parts is called an eighth. Michael got 1 part out of 8. He got 1/8.
1/8.
Right, so Michael got 1 part out of 8. He got 1/8, just one of those 8s. So how many 8s do you imagine that Wayne will get?
3.
Right, Wayne will get 3 of those 8s. So Wayne got 3 parts out of 8. He got 3/8. Brittany got 4 parts out of 8. She got
4/8.
right, she got 4/8, as we can see. So she got 4/8. It is clear who got the most, and that is
Brittany.
Brittany. The correct answer is option C. But do not forget, the problem that we have here were not about an object divided into 8 equal parts. But because we are talking about 8s, we are using a single object divided into 8 equal parts in order that students may understand what we mean when we say 8s. So what about the sweets? We will go to the sweets, no doubt, in a few seconds, as long as or as soon as we demonstrate that Brittany got the most sweets, and that is represented by option C. Remember that the denominator tells us the number of equal parts that the whole is divided into. What tells us the number of equal parts the whole is divided into, Jerry?
The denominator.
Right, so the denominator will tell us the number of equal parts that the whole is divided into. Denominator. So we know that it is divided into 8 equal parts. In this case, the whole has 8 sweets, which represents the equal parts in a whole. See? 8 sweets. That's what we have in the statement of the problem. How many sweets do we have?
8 sweets.
We have 8 sweets. And the whole is divided into how many equal parts?
8.
8. According to the denominator, the whole is divided into 8 equal parts. Therefore, one sweet will represent what? One of those equal parts, right? So there we have our 8 sweets coming up. Each one represents what? One of the equal parts out of 8 equal parts. So the whole is divided according to the denominator into 8 equal parts. And we say that we have 8 sweets. So each one will represent one of those equal parts. The denominator is 8, and we have 8 sweets to represent the 8 equal parts. What do we want? The numerator tells us how many of the 8 equal parts are in the individual share. So we have a share here. This 1/8 is a share, 3/8 another share, and 4/8 is another share. How many 8s are in this share?
1/8.
Right, so 1 is in that share. 1/8. 1 out of the 8 equal parts. How many 8s are in this?
3.
3/8 are in that share. 3 out of the 8 equal parts. And how many in this?
4.
Right, 4 out of the 8 equal parts. So we are focusing now that we have established that we have 8 equal parts. Now we are paying attention to the number of those 8 equal parts that we are talking about. The numerator will tell us how many of the 8 sweets are in each child's share. There we have our numerator highlighted again. Michael got what? 1 part out of
8.
He got 1/8. He got 1 sweet out of 8 sweets. Wayne got 3 parts out of 8. He got 3/8. So he got
3 sweets out of 8.
right 3 sweets out of 8. And Brittany got 4 parts out of 8. She got
4 sweets out of 8.
right. She got 4 sweets out of 8 sweets. The one who got the most got how many sweets?
4.
Right. So this got 1, this one 3, and this one.
4.
Which one represents the most?
Brittany.
With 4 sweets, right?
Yes.
So Brittany got the most sweet, and that is represented by option C. Sanjay had $54 coins in a tin. On Christmas Day, he took out 24 of them. He then put in $18 coins on New Year's Eve. How many coins were in his tin for the new year? So what do we notice? He had how many to begin with?
54.
He took out
24.
and then he put in.
18.
How many coins do we have there?
48. Took out.
Jerry is saying that it is 48. So his calculation is spot on and it is very quick. Jerry, is a person who studies. And please don't tell me that no one can study mathematics, because Jerry studies mathematics and I study mathematics. So he's saying that it's 48. But let us see how Jerry could have arrived at his 48 in a practical sense. Let's go. Let us begin by showing the $54 coins. In the examination, we will not have the time to draw 54 coins, but we will use them to verify our answer. So we are not using the 54 coins to be an example of what you are required to do in an examination. We are using them to verify what we instruct you to do. As a matter of fact, because you are listening to me, you are not counting. So you do not really have to count, because Jerry has included all of those numbers, counting each coin for you. So you do not have to count them. So we have all of those numbers representing the number of coins that we have there. So we are counting or numbering each coin. So, what do we do with those 54 coins? While working out the answer, we will manipulate the coins and take note of the results. There are how many coins in all?
54.
Let us write down the number 54, showing the place values of the digits. So now we are writing and making use of the place values as we promised you in video A. So in the A video, we said that we'll be using place values. Here we go. So we have 54, 5 tens, and 4 ones. 54 coins. On Christmas Day, he took out how many of them?
24.
So you are going to take out 24 of those coins, Jerry, and see what happens. When we take out the 24 coins, will the number of coins get more?
Less.
It will get less. Jerry did not even say no. He went straight to say they will get what? Less. So the coins will get less. So if we take some out, we will get less. So let's see how we make use of that. He took out 24. Let us remove 24 coins. That means we are taking out 24 coins. Jerry said that the number of coins will get less. How do we get less? Alright, let's see. Take them out first. While we are taking them out, we are counting the number of coins that we are taking out. And we take out all of 24. So all of those 24 coins are gone. How many coins are left?
30.
We see plainly that we have 30 here. But we will not do this in an examination. But we are demonstrating that it is going to get less, that is the number of coins, and we are demonstrating that it is also going to be 30 of them. How do we get that 30? The number of coins just got smaller. It therefore means that we need to subtract. So let us take away 24 from 54. So we're going to do our takeaway right there. We will subtract 24 by first placing its ones digit under the ones digit of 54. So here we have 54, 5 tens, and 4 ones. We are subtracting 24. 24 has how many tens? 2 tens and 4 ones. So put the ones digits first, which is the 4 ones, and what do we put next? The tens digit, which turns out to be 2. So place the tens digit of 24 under the tens digit of 54. So we have tens right there. Place the subtraction sign, because when we are subtracting, we make ourselves clear by making use of a subtraction sign. And not only that, we are sure to draw a line to show that we will have our answer below the line. So go ahead and subtract. On Christmas Day, he took out 24. So what do we say? When we have 4 things and we take away 4, what is the result, Jerry?
0.
All right. So let us do the subtraction, beginning with the ones digit. 4 minus 4, and that gives
0.
0. So we have how many diamonds?
4 diamonds.
See, we have our 4 diamonds there. So we need to take away how many diamonds?
4.
So we will take away 4 diamonds. So take away 4 diamonds, what do we get?
0.
Do we have any diamonds left?
No.
No. So there is no diamond left. So the result is 0. 5, take away 2.
3.
Or we say, Jerry saying is 3. Which is correct. Or we may say 5 subtract 2. Or we may say 2 from 5. So let us move to the 10th digit. And when we go to the 10th digit, which is this column that we have right here, we will say what? 5 minus 2, or 5 take away 2, or 5 subtract 2. And the result is
3.
3. So we have 5 diamonds. How many diamonds do we have there, Jerry?
5.
Okay, 5 of them. And what do we do?
Subtract 2 from it.
We will remove 2 of those diamonds. And when we remove those 2 diamonds, what will we get?
3.
3 diamonds. See? So 5 take away 2 gives
3.
3. So how many do we have there now?
30 diamonds. 30.
So we have $30 coins. Right. So we have $30 coins here present, just like the 30 that we have there. Therefore, what we did in arriving at the 30 was correct. The answer is 30, and we also have 30 coins left in the picture. What do we do after we take out 24 of them?
He put back $18 on New Year's Eve.
Okay, so he put in what? 18. So Jerry is telling us that we include another 18. So let us put in 18 of them and see what happens. How do we put in 18? Alright, the instruction is in this slide. So let us see. If he then puts in 18 coins, the number of coins will get
Larger.
right. So let us put in 18 coins. The number that we have here will get larger. If we put in some more, we surely will get more coins. How many of them do we put in?
18.
Right, so we are putting in 18 additional coins. And we are reserving how many places or how many spaces do we reserve for those coins? 18. And then we may put the coins in. So we will put the coins in. So Jerry may be wondering why I decided to put the numbers down, then put the coins there. Because if I put the coins first and then put the numbers here, we need to put another number on top of it, because we need to identify that we are actually increasing the number from 30 to whatever number we are increasing it to. So we put the coins over, because we know already that there are 18 coins that we are adding, because we have the 18 spaces.
Yes.
So we are not in any doubt. But what remains is for us to say how many coins we have in all at the end of it. So how do we do that? If this coin is number 30, then this coin is number what?
31.
Right. So let us count off all of the coins that we now have, beginning where we left off. And where did we leave off?
30.
30, right. We left off at 30. The last numbered coin is 30. Let us begin counting at number
31.
Right. So 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47. And the last one is number
48.
48. The number of coins that he now has is 48. And it is represented by option
B.
Option B. But I think that Jerry should want to add the 18 to the 30 and see what happens. So let us add the 18 to the 30 and see what happens. To the 30 that we have there, which is what we have here, let us add 18. So what do we say? Begin by adding the ones digit. 0 plus 8 will give 8. So place 8 in the ones column. And what is the other one?
1 plus 3.
1 plus 3 or 3 plus 1, and that will give
4.
4. And that will give you your 48 coins. And that will give you your 8 coins. The answer is 48. And the picture has how many coins? 48 coins. So we are verifying that option B is correct. Now we are at problem number 16. What is the value of the underlined digit in 24,321? What is the value of the underlined digit in 24,321? Write down the number 24,321. There we have it. In order to know the value of the digit, we need to be aware of the place value of the digit. And in order to do that, the best thing to do is to include the place values of the digits that we have there. So let us make note of the place value of each digit. In a whole number, one that does not have a decimal fraction, place values begin at the rightmost digit. So let us begin at the rightmost digit. And if Jerry does not know his left hand from his right hand, then we have an arrow showing us what is right. So we have an arrow right there pointing in the direction of our right. So we will begin writing down the place values. And the first one that we have there is our ones digit. Then next beside it, what do we have? Tens digit. Then after the tens digit, we have our hundredth digit. And after the 100 digit, what do we have? Thousands digit. And then after thousands digit, what do we have? The tens of thousands digit. So tens of thousands. How do we know the value of the underlined number? Here we have 3 and it is underlined. What digit does it represent?
100.
It is in the hundreds column. Therefore, it is representing 300s. The underlined digit is in the hundreds column. It represents 300. The answer is option
A.
Option A. 3 hundredths. It is in the hundredths column. It therefore represents 300. There are 25 muffins to be shared among 4 girls. Each gets the same number of whole muffins. How many whole muffins did each get? How many whole muffins did each get? How many muffins in all?
25.
How many girls?
4.
How do we do that? Let's see the approach that we have on our slide. While solving a problem, there may be words in the problem that give us clues as to what to do. What words may give us a clue? Shared and each. When something is shared, or we want to find the number or amount of each, what do we normally do?
Divide.
Alright. So Jerry is spot on that one also. We divide. Or we are required to divide. That is a usual thing. The words may tell us that we should divide. After all, if we have a certain amount or number to be shared among individuals, each one should get less than the total amount. So we cannot multiply nor add, because if we are sharing, each one should get less than the total. We may use the 25 muffins to help us to arrive at our answer. So we are going to manipulate the 25 muffins, and then we are going to do it in an arithmetic way. So let us take a look at the how many muffins?
25.
Jerry is saying 25 because he believes that after this presentation, he will get a chance to eat every single one of those muffins.
Right.
Yes, he's saying that he would be very happy if he could get them to eat. But they are only animations on a screen, so Jerry will not get any. So we have 25 muffins. They are very nice and they look very delicious. Like when we were in primary school, for our break, we always had an option of muffins and something else. That is when we were at Glendevon Primary School. That is where I attended primary school, in Glendevon. We have 5 rows, each containing 5 muffins. So if we have, how many rows do we have? 1, 2, 3, 4, 5. How many muffins in each row? 1, 2, 3, 4, 5. If we have 5 rows of 5 muffins, we do not need to count them. We just say 5 fives equals 25 muffins. Jerry wants those 25 muffins. Shared and each means that we divide, but we are actually going to share them physically and see what happens. So let us represent the 4 individuals. So we have 4 individuals, 4 girls. 25 muffins to be shared among how many girls?
4.
So let us represent the 4 girls. 1, 2, 3, 4. What do we do? Each girl will get a muffin. So we are sharing. So what do? We make sure that each one gets a muffin, right?
Yes.
So we cannot give 2 to one and then give 1 to the other and don't give the other one any. No. So we make sure that each girl gets a muffin. We are sharing. And if we intend that the girls will get the same number of muffins, what do we do again?
Each one, 1.
Give each girl 1 muffin again. Can we now stop and give 1 15 muffin?
No.
No. What do we do then?
Each girl 1 more muffin.
Give them one more, right? So give each girl another muffin. Give them one by one. And then we continue to give each girl another muffin. We will not stop giving them another muffin until what? Right. So give each girl another muffin. Now, Jerry, is it possible to give each girl another muffin?
Yes.
All right. How do we know that we can give each girl another muffin?
Because we have five muffins remaining.
Right, because we have 5 muffins remaining, which is greater than 4. We are sure that each one can still get another muffin. Can we give each girl another muffin?
No.
We cannot give each girl another muffin. Why? Because we have how many girls?
4.
How many muffins do we have?
1.
So we do not have 4 other muffins. We have less than 4. So we cannot give 4 other muffins. So now that we have less than 4 muffins left, each girl will not be able to get one. If we share it for the 4 of them, each one will not get a whole muffin. It can be shared, right? But each one will not get a whole muffin. Let us count the number of whole muffins that each one gets. Count the number of whole muffins that each one gets. Right, how many whole muffins? This one gets 1, 2, 3, 4, 5, 6. And it will be the same number that each one gets. So, the number of whole muffin that each one gets is what?
6.
That is represented by option?
D.
Right, option D is correct. So the correct answer is option D. What do we do with the one muffin? Jerry is saying that we should eat it. One muffin is left. The remainder is 1. So after we divide the muffins for the girls, we get how many whole muffins each one will get?
6.
6. And we have a remainder of 1 muffin that disappears like that. We mentioned before that the highlighted words may give us a clue to how to solve the problem. There we have them again. We are required to divide. So let us divide 25 by 4. So we have 25 to be divided by 4. First of all, we would say what? 4 into 2? We can't. Do we put a 0?
No.
We do not put a 0. And then we say what? 4 into
25.
4 into 25. Division is most efficient when we know our multiplication tables or our times table. We are dividing by 4. So let us use our 4 times table. Jerry, say your 4 times table. You know your 4 times table?
Yes, I do.
Let's go. 4 ones 4, 4 twos 8, 4 threes 12, 4 fours 16, 4 fives 20, 4 24, 4 sevens 28. We can stop right there. So we go all the way up to 4 sevens 28. 4 ones 4, 4 twos 8, 4 threes 12, 4 fours 16, 4 fives 20, 4 sixes 24, and 4 sevens
28.
Right. So if we are about to divide, it is important for us to know our multiplication table. We are dividing by 4. We therefore make use of our multiplication table, our 4 times table. So if we are dividing by a particular number, it is good if we know the multiplication table of that number. So we know our 4 times table it is good because we are dividing by 4. So, we say what? 4 6s 24. Can 4 go into 25 6 times?
Yes.
Because 25 is greater than 24. 4 6 is 24. So 4 can go into 25 how many times?
6 times.
6 times. Can it go into 25 7 times?
No.
4 7s 28. So since 25 is less than 28, we are sure that 4 will not be able to go into 25 7 times. 4 7s are greater than 25, but 4 6s are less than 25. The most whole number of times that 4 can go into 25 is 6 times. The correct answer is option D. So 4 6 is 24. If we subtract 24 from 25, the result will be remainder 1. Therefore, 4 into 25 will be 6 times, or the number of whole times that 4 can go into 24 is 6. And there's a remainder of 1. The canteen counter measures 5 3/10 meters, which shows the length of the canteen counter. So which one of these will be the length? The length of the canteen counter. 5 3/10 meters. We need to pay attention to 5 3/10. Let us write that as a mixed number. 5 3/10. We are just going through a particular process. Maybe someone would want us to go from 5 3/10 into decimals. But if we say 5 3/10, then we are sure that we have a whole number of 5. And what is 3/10? 3 out of 10 equal parts. So that will be 3 over 10. So there we have 5 3/10. What do we notice there? The answers all contain decimal fractions. It means that 3/10 needs to be converted from vulgar form to decimal form. So we will first attempt to convert the 3/10 from vulgar form into decimal form. How do we do that? We are going to be using a short method. We need to divide 3 by 10. Notice that we have what? A single 0 there. We need to divide 3 by 10. The 1 0 that follows the 1 in the number 10 tells us that we need to reduce 3 by 1 place of decimal. So the 3 that we have there will be reduced by how many places of decimal? 1 place of decimal, because we have 1 0 right here. So we first need to locate the decimal point. We are dividing 3 by 10. We are reducing 3 by 1 place of decimal, or 1 decimal place. Now, we need to identify where the decimal point is located in 3. Because if we just put 3 here and there is no decimal point, then we cannot reduce 3 by 1 place of decimal if we do not know where the decimal point is located in the number 3, because for sure we do not have any decimal point right there. So let us now reduce 3 by 1 place of decimal. The result has to be smaller than 3. We may also place a 0 in front of the point, or we say 0 to the left of the point. So we have all of this instruction, but we do not have any process to follow. So we will begin the process. We are about to reduce 3 by 1 place of decimal. So Jerry, will the decimal point be located here or here?
At the front. At the back.
Right. So the decimal point is going to be located, that we say, at the back or to the right. So that is where it is located. In a whole number, the decimal point is located at the right. Right there. And we need to reduce by how many places of decimal? 1 place of decimal. So reduce by 1 place of decimal. So our result is 0.3. A lot of students and mathematicians say 0.3, but I do not say 0.3. I say 0.3. So the 0 is very important. We are paying attention to the format of the answers that we have in the option. The answers are not only in decimal form. Notice they are in decimal form, but they are not only in decimal form. They have 2 places of decimal. So notice that we have 2 places of decimal for each one of them, but how many places of decimal do we have here? 1. We have only 1 place of decimal right there. So let us increase the number of decimal places in the answer to 2 places of decimal. How do we do that? Put a 0 right there. 5 3/10. Now, when we place a single 0 right here, as we said before, a trailing 0 after a decimal fraction does not affect the value of the fraction. The 5 that we have there represents 5 wholes. In a whole number, the decimal point is located at the right. The decimal point also needs to be vertically aligned. We are putting down 5 3/10. We have the 3/10 right here. We need to put the 5 down. But we need to be aware of 2 things. One, that the decimal point in a whole number is located to the right. That is one thing. And 2, we also need to be aware that the decimal points must be vertically aligned. That means one below the other, like that. How many places of decimal do we have? 2 places of decimal. We may include the trailing zeros here, as well as we may not. So include trailing and placeholding zeros, as their presence after the point does not affect the value of the number. So when we put the trailing zeros there to the right of the decimal point, these trailing zeros do not affect the value of 5. The and that we have there means that 5 3/10 are in an addition relationship. So 5 and 3/10 means that they are added together, the 5 and the 3/10. So we will add them, and the result we will see on the subsequent slide. Let us be reminded of the place values of the digits. As we promised, we are including a lot of place values in the problems that we are demonstrating now. Now, after your point, the first digit to the right of your point is the tenths digit. The one, which is the second one, after the decimal point is your hundredths digit. So we have the tenths digit immediately after your point on the right hand side, and we will have the hundredths digit as our subsequent digit. And if we move to another place value here, or another place of decimal, we will have the thousandths digit. We will begin our addition as usual with the rightmost digit, which is the digit of least significant, which is the digit with the smallest place value. That one, the one at the right, that is where we will begin. In this case, it is the hundredths digit. Well, we can add those. 0 plus 0 is equal to? 0. What about 3 plus 0?
3.
What about 0 plus 5?
5.
Do we do that?
No, you have to put down the decimal point.
Okay, so we'll put the decimal point first. So the point needs to be included vertically aligned with the others. So put the point right there, because we are adding numbers with decimal fraction. The decimal point must be included, and it must be included at the appropriate time and place. Next, or finally, we will add the ones or units digit. So we have 0 plus 5, and that is equal to 5. And that, no doubt, will be our answer, and it is represented by what option?
B.
5.30, and it is represented by option B. What do we mean by trailing zeros? Zeros that come after. Those are trailing zeros. So 0.3, in the case that we have a decimal fraction, if we place zeros to the right of that fraction, they will be trailing the fraction, and they will not have any effect on the value of the fraction. So the fraction has the same value as 0.3, no matter how many zeros we put after this 3 or to the right of the 3. It will be what? The same as 0.3. Those trailing zeros will not affect the value of the 0.3. What about this one? Also, if we have a whole number with a decimal point to its right, if we include trailing zeros, they will not affect the value of the number. The number will be equal to 5. So it does not matter how many trailing zeros we have. After that point, it will not affect the value of the 5. If there is no decimal point and we include trailing zeros, what will happen? The value of the number will be affected. The resulting number will not be 5, but 5,000 in this particular case. So if we just put trailing zeros after that 5 without including any decimal fraction or any decimal point, then we will be increasing the value of the number by those numbers of zeros. So we say that this is 5, and if we put 3 zeros there, we are increasing 5 by 3 places of decimal. And students need to understand that decimal does not necessarily mean decimal fraction. But decimal is our number system, and the word deci has the root word that means 10. So when you see decimal, it means base 10, and it means that there are 10 digits in our number system. How many digits do we have in our number system? 10. And we have them 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that's what it means. It does not mean that there's a fraction when we say decimal. It means that the system is base 10. But students and teachers will say decimal when we intend fraction. It is for students to pay attention to the particular case and know what the teacher is saying or understand what the teacher is saying when he or she says decimal. Because we have increased right there 5 by 3 places of decimal, yet still there is no decimal fraction. And when we increase 5 by 3 places of decimal, what is the result? 5,000, right? What do we mean by a place holding 0? The answers have 2 places of decimal, but when we divide by 10, the result had only 1 place of decimal. A trailing 0 was therefore included as a placeholder, so that we can have 2 places of decimal rather than 1, because our option only had numbers that had 2 places of decimal. So we increased the number of decimal places to 2 by putting a trailing 0 or a placeholding 0 there. That 0, does it affect the value of the fraction?
No.
It cannot and should not, because all we are doing is writing the number in another form. Therefore, whatever form that we choose, that form should result in the number being the same or having the same value. 5 is a whole number that we need to add to 0.30. We may go straight ahead and add the numbers as they are. However, the addition process may be made clearer if we include the decimal point and zeros as placeholders. Those placeholding zeros are also trailing zeros. As we will see eventually, zeros sometimes result from especially the process of division. They are sometimes called placeholders, but they are not placeholders. They are actual values, not actual values, but actual numbers that need to be included in the answer. They are not just there for the sake of holding places. They are actually there with some significance, meaning that they contribute to the value of the number. For example, if we have, like on the previous slide, 5,000. Although 0 means nothing at all in terms of its value. 0 means nothing. For example, if we have $0, it means that we do not have any dollar at all. But we cannot say that it does not have any value here, because it has place value, and the 0 here has place value also. Also, this one has place value. If you remove these zeros, then the result is just 5. So the zeros are important, because by including them in this case, instead of having just 5, we have 5,000. Those placeholding zeros are also trailing zeros. As we will see eventually, zeros sometimes result from especially the process of division. They are sometimes called placeholders, but they are not. Carlene was the 4th person to cross the finish line in a race. Joy Ann was the person who crossed the line just in front of her. Just in front of her in the nick of time. In what position did Joy Ann finish? So there we have our finish line, And there we have the girls crossing the finish line. Let us count the girls in the order in which they crossed the finish line. I hope that it is not difficult to remember the order in which they crossed the finish line. So we will count the girls in the order in which they cross the finish line. So let's count them. 3, 5. Right. So 1, 2, 3, 4, 5 of them. So the order in which they cross, this one, then this one, after that, and this one, and this one. So this one crossed the finishing line first. The order may be given in ordinal numbers as follows. So we have ordinal numbers, and those numbers tell the order in which events occur. So position 1 is called first, and it is written like that. Position 2 is called second, and it is written like that. Position 3 is called third. Position 4 is called fourth. Position 5 is called fifth. So there we have the girls and the position in which each one finished, or each one crossed the finish line. So the one in position 1 is first, in position 2 is second, in position 3 is third, position 4 is fourth, position 5 is fifth, and so on. So numbers like first, second, third, fourth, fifth, and so on are called ordinal numbers. They tell us the order in which events occur. Carlene was the fourth person to cross the finish line. Can we identify the fourth person?
Yes.
Okay, and that person will be identified as Carlene. Carlene was the fourth person to cross the finish line. Joanne was the person who finished just in front of her. That's Joanne. Joanne finished just in front of her. What does that mean? Just in front of her.
She's the fourth. The third.
Okay, she will be the
Fifth. The fifth.
Joanne was the person who finished what? Just in front of her. Right. Carlene is fourth, so Joanne will be third. That's Joanne. How do we know? Because if we go back to the order in which they cross the finish line, we realize that this one is in 1, this one is 2, this one is 3, and this one is 4. Carlene crossed fourth. Joanne was just before, so she is at third. She therefore finished in third position. The correct answer is therefore option D. Some persons confuse ordinal numbers. They mix up the size of the number and the positions. They mix up what? The size of the number and the position. How do they mix them up? The high positions are represented by the small ordinal numbers. So if we have a race and someone finished in fourth position, then there's someone who finished higher in the race. That does not mean a larger number. It means a smaller ordinal number. So if the person is higher up in the race, then that person will finish in a smaller ordinal number. So the highest position are represented by the small ordinal numbers. The highest position is first. Also, the lowest position is associated with what? The largest ordinal number. In the race, the lowest position is fifth. So if you finish in a very high position, it means that your ordinal number is small. And if you finish in a low position, it means that your ordinal number is large. And the one that finished just before you or better than you, that person will have a smaller ordinal number than what you have. So if you finish 5th and someone finishes ahead of you, then that person will be in a smaller ordinal number position. And if you are at 2nd and that person finished in a lower position than you, then that person has a larger ordinal number. 6 cakes were cut into quarters. How many quarters is this in all? So 6 cakes. We have all 6 cakes. And they are cut in quarters. What do we mean by a quarter? 6 cakes were cut into quarters. A quarter is 1 part out of, well, it is 1 part of a whole if the whole is divided into how many parts? For a quarter, the whole must be divided into how many parts?
4 equal parts.
4 equal parts. Right, so the whole must be divided into 4 equal parts. So the numerator, the fraction bar, and the denominator, we always going to have those from time to time. So the denominator is 4. And that tells us that the cake is divided into
4 equal parts.
So each cake is divided into 4 equal parts. The denominator tells us the number of equal parts that the whole is divided into. So the whole is divided into how many? 4 equal parts. So let us divide each cake into 4 equal parts. So the first cake is divided into 4 equal parts, and the second is divided into, and you imagine that the third will be divided into
4 equal parts.
Right, and we will continue to divide those cakes into how many equal parts?
4 equal parts.
Until we have all of the 6 cakes divided into 4 equal parts. So if we have 6 cakes divided into 4 equal parts, how many quarters do we have in all?
24.
How many of those 4 equal parts do we have in all? And Jerry is saying that we have 24. How did you get 24, Jerry?
We multiply the 6 quarters of the cake by the 6 cakes.
Okay, so you take the cake that have what? The quarters here, and we know that we have 6 cakes. So we know that 1, 2, 3, 4, and there are 6 of them. 6 fours, 24. That is how Jerry arrived at his conclusion or his answer. But if we attempt to count them, what will happen? So let us find out the number of quarters in all by counting the total number of quarters in the 6 cakes. So Jerry said that we have 24 quarters in all, and we are actually counting them. But Jerry said that he did not count them. He said that we have the cakes divided into 4 parts, and there are 6 of them. So 6 fours, 24, which is correct. So how many of those quarters do we have? 4, and that is represented by?
Option D.
Right, so there are 24 quarters in all. The correct answer is
Option D.
option D. We are at the same problem. Let us take another approach to the problem. There are how many cakes?
6 cakes.
6 cakes. They are cut into quarters. So the cakes are cut into quarters. We need to know how many quarters. We may say that the cakes are divided into quarters, and as such proceed to divide 6 by a quarter. So let us explain that. The cakes are cut into quarters. We need to know how many quarters. We may say that the cakes are divided into quarters. Is that right?
Yes.
The cakes are divided into quarters. So we may say that the cakes are divided into quarters. How many quarters do we have, or how many cakes do we have?
6.
We have 6 cakes. Therefore, we are dividing the 6 cakes into quarters. So the result that we get for our answer may be found by dividing 6 by a quarter. So we are saying quarter into 6, or 6 divided by a quarter. On the other hand, we are really attempting to determine the number of quarters that are in 6. How many times may a quarter go into 6? Or how many quarter cakes are in 6 cakes? How many 5s are in 20?
4.
4. How did you get that?
Because you divide
5 into 20. Right. So we divide 5 into 20. How many 5s are in 20? We say 4. 20 divided by 5 is equal to 4. So how many quarters are in 6? We say 6 divided by a quarter. It is the same question using different numbers, and the result is obtained in the same way. So how many times may a quarter go into 6? Or how many quarter cakes are in 6 cakes? We do that by dividing 6 by a quarter. When working fractions and whole numbers, the whole numbers are written as fractions with 1 as the denominator. So this whole number may be written as a fraction because we are manipulating fractions, and it may be written as a fraction with 1 as the denominator. Also, when dividing by a fraction, we invert and multiply. So invert which fraction? The one that we are dividing by. What another word for invert in this particular case? Reciprocate. So we will find the reciprocal of a quarter. It means that we will reciprocate a quarter. So we are dividing by a quarter, so we invert and multiply. So what is the result? 6 4 is 24, as Jerry pointed out. When multiplying fractions, we first see if there is any common factor that we may use to reduce the fractions. Meaning, if there is any number that can cancel. The denominators are equal to 1. The fractions cannot be reduced. Because when we are reducing fractions, we usually reduce that fraction by a common factor. That is, a number that can go into the numerator and go into the denominator without leaving a remainder. And if we choose 1, 1 will get us nowhere, because if we divide 4 by 1, we will get 4. And if we divide 6 by 1, we will get 6. The answer will be the result of, well, since we cannot reduce the fractions, then we go straight ahead to find our final answer. The answer will be the result of dividing the product of the numerator by the product of the denominators. So, to find the answer, because the fractions cannot be reduced, we multiply 6 by 4, and we get what? 24. And what do we do next? We multiply the denominators next. 1 multiplied by 1 will give 1. Right. So, multiply the numerators, 24. Multiply the denominators, 1. What do we do after that? We divide 24 by 1. Any number divided by 1 is equal to the same number. So any number divided by 1 is equal to that same number. So 24 divided by 1, what will that give?
24.
That will give us 24. And that verify our answer to be option D. So the correct answer is option
D.
Right. We have our problems and we have our 6 cakes already cut into quarters. But Jerry does not want his cake to be cut in quarters. He wants the entire cake for himself. So 6 cakes cut into quarters. We could have taken a look at our diagram and made a conclusion. We could have taken a look at our diagram and make a calculation based on what we have in the diagram. Each cake has 4 quarters. 4 quarters we have in each cake. How many times do we have 4 quarters?
24.
How many times do we have 4 quarters?
6 times.
Right, because we have 6 cakes. We have 6 cakes, so we have 4 quarters 6 times. So there are 6 cakes. We therefore have 4 quarters 6 times. 4 quarters occur 6 times. We therefore times the 4 by 6. And I'm using the word times because I want to be consistent with what I've said before. So instead of saying we multiply the 4 by 6, we times the 4 by 6. And if we multiply 4 by 6, what do we get?
24.
4 6s, 24. And we are still with option D as our correct answer. Which shows 15 and 2/10 as a decimal? Which shows 15 and 2/10 as a decimal? 15 and 2/10 means 15 wholes and 2 parts out of 10. We may express it as a mixed number. So we have 15 and 2/10 mean what? 15 wholes and 2 parts out of 10. 15 and 2/10. There is no vulgar fraction in the options. Let us convert the vulgar fraction to decimal fraction. So the vulgar fraction that we have there is 2/10. We need to divide 2 by 10. The 1 0 in the number 10 tells us that we need to reduce 2 by 1 place of decimal. So we have done that before, reducing a number by 1 place of decimal. So reduce 2 by 1 place of decimal. In a whole number, the decimal point is at the right. So we will reduce 2 by 1 place of decimal. 2, the decimal point is located at the right. So reduce that by 1 place of decimal. Place a 0 in the whole number position. There it is. 15 is to be added. Its decimal point is at the right. So in a whole number, the decimal point is located at the right. And it must be vertically aligned with the decimal point in the other number. So there we have it, 15. So 15, the decimal point must be to the right of 15 because it's a whole number, and it has to be vertically aligned with the other decimal points. And now we will add we will begin our addition with the rightmost digit. In this particular case, notice that we are not including any placeholding 0 or any trailing 0. So let's go. We will begin our addition with the rightmost digit. A blank space below the 2 means that nothing is to be added. If we do not add anything to 2, what will be the result? This is the same thing as saying 2 plus 0, which is 2. What do we do next?
Put down the decimal point.
Right, so the decimal point must be vertically aligned. So vertically align the decimal point. There it is. Right there. Then move to the ones or units digit. What do? We are going to add the units digit. 0 plus 5 is equal to 5. And we do not have anything to be added to that 1. Finally, add the tens digit. Add the tens digits. The blank space means that nothing will be added to the 1 that we have here. So nothing which is the same as 0 is added to 1. So 0 plus 1 is equal to 1. So when there is nothing occupying the space, then we will add 0. Or we will just write the number down, because if we add 0 to, say, 7, the answer is 7. So if we have a blank space above 7, we'll just write 7 down. We may add without placeholding or trailing zeros by making use of the fact that the value in an empty space is equal to 0. A trailing 0 after a decimal fraction does not affect its value. Right there. So our answer is 15.2, but what do we have here? 15.20. So candidates need to be aware that if we include a trailing 0 after a decimal point, it will not affect the value of the answer. So 15.2 we got, which is the same thing as 15.20, and 15.20 is the one that is in the options. So what option is correct?
C.
The correct answer is option C. When counting by hundredths, which number comes just after 99? When counting by what? Hundredths. What do we mean when we count by hundredths? We are counting by hundredths. Place values are therefore important. So when we are counting in hundredths, or by tenths, or by tens, or by hundreds, place values are very important. So we have 99, and we have what here? This is our ones digit, and this is our tens digit. But we will be counting by what? Hundredths. Hundredths. We need to include the hundredths place value in order to solve the problem. Because we are looking at the number that comes just after what? 99. But we are counting what? In hundredths. Therefore, what do we have here? Ones and tens. We do not have any hundredths. So, in order to proceed, we need to include the hundredth place value. We need to include the hundredths place value because we are counting by hundredths. Counting by hundredths will cause the hundredth place value to increase by 1 each time. So if we are counting by hundredths, this is the place value that will be affected directly. So 1, 2, 3, and so on. We are counting in or by hundredths. Therefore, the hundredth place value is the one that will be increasing by 1 each time. When counting by hundredths, the number that comes just after, next after, or immediately after 99 is 99.01. Why is it that it is 99.01? Because 99 is exactly the same as
99.00.
right, it's exactly the same as 99.00. Why do we need to include the 2 zeros? Because we are counting by hundredths, right? So we need to include the hundredths place value. And if we just include 1 0, what will happen? We will only have tenths. So if we just put a single 0, we have tenths, but we will not have hundredths. So in order to have the hundredths place value, we need to include the tenths place value, then the place value, right? So we include those two. So counting by hundredths will cause the hundredth place value to increase by 1 each time. So that one will increase each time. And we can see that which number will come immediately after 9.00. Which number will come immediately after 99.00, which is the same thing as 99. Which number will come after 99? That number is the same number that will come after 99.00. And if we are counting by hundredths, the hundredth decimal place is the one that will be increasing each time. So there it is. It will be 99.01 because it goes up by 1 each time. But what I've done is to show you that when we are counting by hundredths, that we keep on increasing the hundredth place value each time. And what will happen in a subsequent presentation is that we will show you when these digits increase up to 9, what will happen. And that will be very exciting, very interesting, very informative, and everyone will learn something additional when we get there. When counting by hundredths, the number that comes just after or next after or immediately after 99 is
99.01.
right. So that is our answer. The correct number is therefore represented by option A. Jerry has 20,000 rubber bands in a bag. How many?
20,000 rubber bands in a bag.
Who has that?
Jerry.
Okay, Jerry, you have 20,000 rubber bands in a bag. That's a lot of rubber bands. Which of these shows Jerry's total number of rubber bands? Is it 20 bags of 100 rubber bands? 20 bags of 1,000 rubber bands? 100 bags of 2 rubber bands? Which one will show Jerry's total number of rubber bands?
20 bags of 1,000 rubber bands.
Right, so Jerry is saying it is 20 bags of 1,000 rubber bands. 20,000, 20,000, 20,000, 20,000, 20,000. Therefore, option B is correct, and that would have been pointed out by Jerry. As a matter of fact, Jerry has the 20,000 rubber bands, so he should not have any difficulty telling us how he arrived at his 20,000 rubber bands. But what we will do, we will demonstrate, just in case the numbers are not so easily manipulated, how we could arrive at our answer. Now, what we have here, because we could not possibly include 100 rubber bands or show that in 20 bags on this screen, we are going to use a manageable number of bags and a manageable number of rubber bands to determine how we will manipulate these numbers that we have here in order to arrive at 20,000 rubber bands. So we will use a smaller manageable number in order to come to the conclusion as to how we will manage these larger numbers. So what do we have here? If we have 3 bags, each containing 4 rubber bands, how many rubber bands do we have in all? We have,
16.
let's go again. We have 3 bags containing how many rubber bands?
4, 12.
Alright, so we have 12 rubber bands. Let's see how we could work with that. That is your first bag, and we are taking the rubber bands from the first bag. Do we have another bag? Yes, we have a second bag, and we are taking the rubber bands from that one. And then we have what? Do we have a third bag?
Yes.
Yes, we have a third bag, and we are taking rubber bands from the third bag, and we have all of the rubber bands represented there. As a matter of fact, Jerry just mentioned that if we have 3 bags, each containing 4 rubber bands, Jerry said that it is how many rubber bands in all?
12.
How did you arrive at that 12, Jerry?
Because 4 is in each bag and there's only 3 bags.
So what do you do with the 4 and the 3?
Multiply.
Okay, so Jerry multiplied the 4 by the 3, and he got his 12. So what do we know? We may count the number of rubber bands, because we can count them. As a matter of fact, we removed the rubber bands from the bags, or we copied them from the bags. So we have how many rubber bands in all?
12.
12. Now if we have 3 bags containing 4 rubber bands, which arithmetic operation involving 3 and 4 did we use to get the answer? And Jerry said that a long time ago, but I'm going to ask him again. I'm asking him again. What operation did we use with the 4 and the 3 in order to get 12?
Multiply.
Right, so we use multiplication. 4 3s, 12. So take a look at the possibilities. We have 3 plus 4, and that is equal to 7. So it is not addition. 3 times 4, and that is equal to 12. So we are sure that it is multiplication. So we multiplied. Why am I using 3 bags of 4 rubber bands to determine that we need to multiply? Because if we have 20 bags of 100 rubber bands, it means to determine how many rubber bands in all, we will need to multiply also. So if we multiply 3 bags by 4 rubber bands in each bag, we got 12, which is the total number of rubber bands overall. So in order to get the number of rubber bands, 20,000, it means that the numbers that we have in each option will be multiplied. So we will multiply the 20 by the 100, or 20 by 1,000, and so on. Multiplying will give us the correct answer. So multiplication is what will give our correct answer. Therefore, we will have to multiply in the options that we have there. The result of 3 bags of 4 rubber bands was obtained by
multiplication.
Right. Those in the options should multiply, therefore, to give 20,000. Right. So we have concluded that multiplication is what we need to use. So 20 bags of 100, 20 times 100. There is a simple way to multiply numbers that have trailing zeros. So when we multiply these, whatever we get, if we get the 20,000, then that option will be correct. But we knew already beforehand what the correct answer will be. However, we are demonstrating all that we can, making use of the fundamental principles that students may be able to handle themselves when they come across other situations that are not exactly like this, or that were designed for you to think and operate. You cannot, as smart as you are, solve a lot of problems in mathematics if you do not understand fundamental principles. So we have 20 bags of 100. And what did we say that we need to do with those 20 and 100?
Multiply.
So we multiply. So 20 times 100, how do we arrive at the answer? Let's see. There is a simple way to multiply numbers that have trailing zeros. When we are multiplying numbers and we have a lot of zeros following, there's a simple way of doing that. First, multiply the significant digits. They are the leftmost non-zero digit. Therefore, the significant digits are the digits that are in each number, the digits that are to your extreme left. So in this 20, what is the significant digit?
2.
The significant digit is 2 in this case. And what is the significant digit in 100?
The 1.
Right. The 1 is the significant digit because in this number, the 1 is at the extreme left and it is not equal to 0. So when we are talking about the significant digits, we are talking about those digits that are not equal to 0. Non-zero, not equal to 0. So in this particular case, what is the non-zero digit? The 1, and it is at the extreme left. Also in the 20, 2 is the significant digit. It is to the left and it is not equal to 0. So first, multiply the significant digits. What are the significant digits? 2
and 1.
Okay, 2 ones. So those are the significant digits. When you multiply them, what do you get? 2 ones?
2.
Right, so 2 times 1 is equal to 2. So 2 is going to be in your answer. Is that all?
No.
Okay, because there's no way you can multiply 20 by 100 and the result is 2. After that, what do we do? The answer will have the same number of trailing zeros as in the numbers that we multiplied. What are the numbers that we multiplied?
2 and 20 and 100.
Right, we multiplied 20 and 100. So the number of zeros that we have will have the same number of zeros as in the 20 and the 100. So Jerry, how many zeros do you see?
3.
Okay, so we have 3 zeros here. That means your answer will contain how many zeros?
3.
Right. So we have 3 trailing zeros in the numbers that we are multiplying. Therefore, we will have 3 trailing zeros in the answer. So 1 will go over 2, 3. So we have 3. So we have 1, 2, 3 trailing zeros. And we have how many here? 1, 2, 3 trailing zeros. So this number with the 3 trailing zeros, what is that number?
2,000.
Right, that number is 2,000. And what do we have here?
20,000.
So is it that option A is correct?
No.
No, option A is not correct. As a matter of fact, I am only using option A as a demonstration as to how to multiply numbers with trailing zeros. What did your old teacher tell you that off means when you have off in your mathematical problem? Well, my old teacher, he said that
Multiply.
off means that you
Multiply.
right. Off usually mean that we multiply. So we were instructed by our good old teachers that when we see off, it usually means that we should
Multiply.
multiply. So it is not that we needed to the extent that it would have been the only way to use the 3 bags with the 4 rubber bands, but it is a practical demonstration, and practical demonstrations are good because it convinces you that you are doing the right thing. However, we know, and we could have, without going that route, use the fact that we have off here to mean that what we really need to do is multiply. In all cases, the significant digits will multiply to give 2. So, significant digit 2 ones.
2.
2 ones.
2.
1, 2.
2.
2 ones.
2.
So, in all cases, the significant digits that we have there will multiply to give 2. So, we have that 2 ones 2, 2 ones 2, 1 times 2, 1 times 2 is 2, and 2 ones 2. Now, here's our question. So, we have no doubt that the significant digits in each case will multiply to give 2. And what is the significant digit in this case? Jerry?
The 20. The number 2.
Right. So the 2 is the number that is the significant digit right there. The 2, and we have no doubt that we are ready to get this number. Now, since all of the significant digits multiply to give 2, which one is the correct answer?
Option B.
Why is it that option B is correct? Because here we say, in which option will the total number of trailing zeros be the same as in 20,000?
Because there is 20 bags of rubber bands. So you say 20 times 1,000 rubber bands, and that will 20 times 1,000 rubber bands, and that will give you 20,000.
Okay, so 20 times 1,000, and that will give you 20,000. Now, what we are paying attention to in this particular case, because the significant digits are all the same, is the number of trailing zeros. There are 4 trailing zeros in 20,000. Is that right?
Yes.
In 20,000, how many trailing zeros do we have? 4. The one that will give the correct answer should have how many trailing zeros?
4.
Which option has a total of 4 trailing zeros?
Option B.
Right, so we have 1, 2, 3, 4 trailing zeros. So 20 bags of 1,000 rubber bands. And there we have the number of trailing zeros. And how many trailing zeros do we have?
4.
And how many trailing zeros do we have in 20,000?
4.
Right, so that one will give us the correct answer? The correct answer is option
B.
right. That is our correct answer. The significant digit turns out to be the same in all cases. 4 trailing zeros. Here we have 1, 2, 3, 4. A total of 4 trailing zeros. Apart from the off that is present, that gives an indication that we should multiply, if we have a certain number of objects that occur a certain number of times, the total number of objects may be determined by multiplying. So if we have a certain number of objects occurring a certain number of times, then the total number of objects will be determined by multiplication. For example, if we have 7 boxes containing 3 eggs in each box, how many eggs do we have in all? 7 boxes containing 3 eggs in each box. How many do we have in all?
21.
Right, because 7 threes, 21. So the number of eggs will be determined by multiplication. The word times is also used for multiplication. Right, our teacher always say times also. So times is also used for multiplication. Which of these represents a line segment? Which one of these represents a line segment? Now, this is a serious problem and a serious issue overall, because we call line segments line, and we imagine that when we draw our line, that the line will end somewhere. But a line does not end at all. But line segments do have ends. So let us take a look at this one. Each of the diagrams on the left is related to a straight line. In the diagram of a straight line, there are arrows at each end that go in directions away from each other. So in the diagram of a straight line, we have what? Arrows. Where are the arrows?
At each end.
And they go away from each other. That is the diagram of a line, having arrows at each end, and the arrows go away or pointing away from each other. So that is the diagram of a straight line. Those arrows indicate that a line has no end. It continues indefinitely in both directions. Indefinitely means it will continue on and on and on and on and on and on. So it will continue indefinitely in both directions. Others may say that a line continues to infinity in both directions. Option C is a diagram of a
Straight.
line, as you can see, with the arrows at both ends that point away from each other. That is the diagram of a straight line. Which of these represents a line segment? Which one of these represents a line segment? That is the problem. Which of them is a line segment? A line segment is a segment or a section of a line. A line segment is a line segment has a definite or fixed length. It therefore means that the length of a line segment may be measured, while the length of a line cannot be measured. So the line segment is just a portion of the line. It may be segmented from the line or cut off from the line. That is what we call a line segment. It has a definite length. It is a portion that is cut off from a line. A line segment is a portion that is segmented, cut off, or removed from a line. The most notable features of a line segment are its two endpoints. The segment is the region between those 2 points. The points are very important because they show where the segment ends. Although they are important, we may also determine that we have a line segment if those 2 large points were not seen. So there we have a line segment. A portion that is cut off or segmented from a straight line. And for the line segment, we have 2 enlarged dots showing that these are the 2 endpoints. But we will see later on if and why they are necessary. That is your line segment. And your line segment, Jerry, is in what option?
Option A.
Right, so line segment is in option A. Option A is the one which represents a line segment. So there's your line segment, Jerry. Option A. Well, it is good if we do not just say that this is a line segment and this is a line, and then we do not know what the others are. Option B represents a ray, like a ray of light. It represents a ray. A ray is like a beam of light when you turn on a flashlight. It is emitted, it emanates, or it emerges from one single point. The direction of the ray is always away from that fixed point. So let us put our ray down. Notice what happens. It begins at a point and it continues like that. Does it have any end? No. This one will continue indefinitely, and as Jerry said, it will continue and on and on. Right. So that one will continue on and on and on. So it does not have any end right here. But right here is what we call the beginning point of the ray. So it has a beginning point. So it begins right there and continues forever. So that is a ray. The diagram of a ray contains a single point and a single arrow. The point shows the beginning of the ray, and the arrow shows the direction in which the ray is traveling. The ray continues indefinitely, or some may say to infinity, in the direction of the arrow. A ray, therefore, does not have a fixed length. Its length cannot be measured. So it will continue indefinitely, but in one direction. Option D is a ray, but the beginning point is not obvious. So this is also a ray. This one is obviously a ray because of the beginning point, but this one, we do not give it an obvious beginning point. But let us see why it is still a ray. Line segment. A straight line is a collection of points. Right. A straight line is a collection of points. The points are placed so close to each other that there is hardly any difference between them, and that is why they form a straight line. The points are beside each other, so close that there is hardly any difference between or distance between the points. And that is why we have the straight line with that collection of points being so close to each other. So a straight line is a collection of points. Therefore, it is not always necessary to show the end points of a line segment. A line segment always ends at 2 points, whether or not we indicate them with large dots. So if we take away the large dots, what we have there is still a line segment. Why? Because a line is a collection of points. Therefore, we must have a point here and we must have a point there. So we do not have to represent them with large dots for them to be considered to be points. The ray, what about the ray? A straight line is a collection of points. We are mentioning that again. Therefore, it is not always necessary to show the beginning point of a ray. A ray always begins at 2 points, whether, let's take it out. A ray always begins at a point, whether or not we indicate it with a large dot. So a ray has a single beginning point, and the point is always there, whether or not we use a large dot. Why? Because a line is a collection of dots or points, right? So a line is a collection of points. So right there, we are sure that we have a beginning point. However, raised and straight line must have their accompanying arrows. This one cannot be a ray without the arrow here. And the straight line cannot be a line unless the arrows are at both ends. So although we do not have to use the enlarged dots to show the beginning or end points, we are sure that if we have a ray and a straight line, we must have their accompanying arrows to show the directions of travel. The arrows must be there to show that the line continues in both directions and a ray continues in a single direction. So we have to have, if we have line segment, if we have a ray, we have to have the single arrow showing that it continues indefinitely, and we have a straight line, then we must have the arrows showing that the line continues indefinitely. So the straight line and the ray must have their accompanying